Variable frequency drives, or inverters, have been used for years on fans for capacity control. As buildings strive to improve efficiency while maintaining comfort, inverters have been applied more frequently to compressorized systems as well. Variable refrigerant volume systems, ductless split systems, and packaged rooftop units all utilize this technology. Inverters allow capacity control and load matching. Capacity control is achieved by changing the electrical frequency going to the compressor or fan motor, which reduces the speed and energy consumption. When a vapor refrigerant travels through a compressor, it increases in pressure and temperature, increasing the energy within the refrigerant. Now, the difference between the temperature leaving the compressor and the temperature entering the compressor is called lift. The higher the lift, the more energy is required. Inverters slow down the compressor, reducing the lift and energy use. In addition to reducing lift, the compressor speed is also reduced, lowering the amp draw of the compressor at part load conditions. Since the compressors are running slower at part load, less refrigerant gas is compressed, thus outputting less capacity. This is why inverter compressors are excellent at load matching. The result is better control and more comfortable spaces. Inverters can be applied to most compressor types. Before the development of inverter-rated compressors, load matching was accomplished through several other methods. As we discuss these methods of compressor staging, remember how efficiency is calculated. So efficiency equals output capacity divided by input power. By definition, reducing the capacity with full power input decreases efficiency. These are the methods commonly used for compressor modulation. Staging multiple compressors is the simplest method of capacity control. Staging compressors result in larger temperature swings as compressors fire on and off. Single or dual compressor units will see the largest temperature swings, and units with more compressors will have tighter control. Hot gas bypass diverts hot refrigerant vapor around the evaporator coil through an external mechanical solenoid valve, allowing the compressor to operate at low loads. While this accomplishes part load operation, it is inefficient since the compressor is still running at 100% speed and compressing the same volume of refrigerant. This inefficiency is why most codes have placed limitations on the use of hot gas bypass. Dual-stage compressors are used on small single compressor systems to reduce the temperature swings seen with staging a single compressor. Dual-stage compressors bypass a portion of the refrigerant gas in the scroll back to the suction side, reducing capacity. Two-stage compressors typically have 65% and 100% capacity steps, although the compressor is running at fixed speeds. Digital scroll compressors use the concept of hot gas bypass and integrate it into the compressor. The compressor can separate the scrolls within the compressor, allowing the refrigerant to bypass the compression cycle, thus reducing the compressor output at a low speed. Digital scroll compressors use electronics within the compressor to reduce the output while running at a fixed speed of 100%. Like hot gas bypass, digital scrolls offer part load operation and load matching, but at reduced efficiency. Inverter technology is also applied to the condenser fans, resulting in lower energy consumption at part load speeds. This optimizes load efficiencies, reduces sound levels, and allows low ambient operation. As our industry continues to push for higher performance buildings while optimizing comfort, inverter technology will continue to be an essential piece of the puzzle.